Okay, so good morning or good afternoon to everyone. Today's speaker for the seminar is Artur Piękosz from Cracow, and he will talk to us about gluing together definable sets.
Okay, thank you. So I want to thank the organizers for allowing me to present this talk. And which no. Can you see the second slide? Yes, I think.
Yes.
So in the 80s, two German mathematicians, Dels and Knebusch, showed how to glue together semi-algebraic sets. So I want to extend this theory to a general setting, and for the beginning, just look that that definable and relatively open subsets are very important in other contexts. So my first structure, which I want to define to somehow develop needed topology for gluing together definable sets, because usual topology is not enough. So some kind of a generalized topology will. Okay, so a locally small space with some family of subsets such that the empty set is in this family. It is closed under finite unions and intersections, and it is covering the set. So members of this family Lx will be called SMOPs because they're intended to be small open subsets. And Lx, if needed, will be denoted LSO, small opens on X. So for example, if we have a real line, we can consider several possibilities of defining a smopology, right? For example, if we take the family of finite unions of open intervals, it will give us the minimal real line, but we can choose the family of finite unions of bounded open intervals. So those will be SMOPs, and so we get the localized minimal real line, right? We can choose L-SLOM, so the family of all locally finite unions of bounded open intervals, or we can restrict not all intervals, but with real endpoint, with rational endpoints, for example. So there are several many possibilities of defining a smopology, giving the same topology. It already was used, this symbol O. It's important because if I have a smopology, then I can produce the family of all open sets. LXO are the sets which are compatible with SMOPs. A set B is open if its intersection with a SMOP is a SMOP. Okay, so I have two families of subsets, and of course I can generate a usual topology, but those sets will be not important for me. I call it weakly open, and functions that are continuous in the traditional sense, I call only weakly continuous. But the idea is that they are not important. As space is small if the whole X is a SMOP. Okay, so for each topological space, for example, for a real line with natural topology on the real line with a Sorgenfrey topology, I can produce many smopologies giving the same topology. So as we see, the axioms are that we assume not all, but only some conditions needed for a topology. So it's a kind of generalized topology, but in fact, it's better to treat smopologies as topologies with additional structure. So smopologies not only give topology, but also give these open sets in the strong sense, some basis of the topology, distinguished basis, and also give Bornology. Okay, so I want to get a category. So what are morphisms? Morphisms are maps that are bounded. So smopology in the domain refines the preimage of the smopology in the codomain, and continuous, which means that preimage of the smopology in the codomain is compatible with the smopology in the domain. And I get the category LSS, earlier named sublat, locally small spaces, and bounded continuous maps. And it's a full subcategory of small spaces. Okay, I will need sometimes to restrict to T0 spaces. So smopology separates points as usual if 2 points belong to the same elements of the smopology, they are equal, right? So this is T0 locally small spaces, and T0 small spaces give me such categories. And I can describe what it means to be admissible. An open family is admissible if it's locally essentially finite, right? So what this means? It means that for each member of the smopology, the restriction admits a finite covering of its union. So I will say the restriction is essentially finite. Okay, one needs to be careful about admissibility. For example, if we have two families with the same union, and if we know that the larger is admissible, then the smaller may not be admissible. Also, if we take intersection of two admissible, the intersection may not be admissible, right? On the other hand, this larger family with the same union is always admissible, is not smaller. So they are closed under coarsenings, not under refinements. Okay, the example is the following. We have an increasing sequence of open intervals, the union of this family, and an even larger set. So this families U union V and U union W are admissible because there is the largest set in each of the family. But if we take the intersection, it's not admissible. It's not essentially finite. Okay. So we can distinguish an important factor from locally small spaces to small spaces. Take this LXO as a new smopology, and it appears that it is a reflector, right? So it's an important factor. It's wrong just to to add X as a member of the homology. This has wrong, this is bad categorical properties, but this is the right way. Okay, and we have a theorem on concrete isomorphisms, because concrete isomorphism between locally small spaces and the earlier category, which was used by Delft and Knebusch, right? This category of generalized topological spaces had 8 axioms and also used indexed families of subsets. And so it was first simplified to 5 axioms, but now, if we restrict to locally small spaces, it's just the definitions which we have above that are enough. So maybe I will not describe this GTS because it's a kind of monster if time allows. I will do this, but okay, so if we have a set with a homology, we can produce a generalized topological space taking LXO and this family, subfamilies of LXO, so open sets, which are essentially finite on members of LX. And vice versa, if we have a GTS, which is locally small, we just get the family of small open subsets of X. And these two functors give the isomorphism. They are inverse to each other. Okay, now we want to pass to the definable spaces, right? So we need some additional category, ambient category, in which the locally definable spaces will be contained. So I think that the function sheaf should stay in the definition to have a good definition which is coordinate free. So a function sheaf over a set is a family of functions. Domains are open sets, and this family is closed under restrictions to open subsets and to closed under gluings of compatible families of functions defined on members of an admissible family. And for such function sheaves, I have the operation of taking image and pre-image. So a locally small space over M is a pair, a locally small space and a function sheaf over M, right? Morphisms are such functions that are bounded continuous, so morphisms of locally small spaces, and also the condition with function sheaves. Pre-image of a function sheaf in the codomain should be contained in the function sheaf in the domain. So I get this LSS of M. Now we build locally definable spaces by pieces. One piece is a definable set. So the context is the following. I have any structure and any topology on the underlying set, even not contained, not connected somehow to the structure, and I have a definable set D, so I can get all relatively sigma open M definable subsets as the homology, and all sigma continuous M definable functions as the function sheaf. So this is an object of LSSM, and affine definable spaces are objects of this category which are isomorphic to objects of this type. Now, definable spaces are such objects of LSS of M which admit an open finite covering by objects of the category of affine definable spaces, and locally definable spaces is the category generated by object admitting an admissible covering by objects of the category of affine definable spaces, right? Okay, if sigma is somehow definable in the structure, we can omit sigma. We have just LDS of M. And in the special case of omnium expansions of real closed fields R, we have the theory of locally definable spaces, right? In particular, a homotopy theory for regular paracompact locally definable spaces. So this was developed in this monograph by Delft and Cracow, locally semi-algebraic spaces in '85, and it was extended to locally definable over omnium expansions in this Rocky Mountain paper, right? And we can completely change the definition into this, the above definitions. We don't need to use generalized topology at all. Okay, so let's pass to weakly definable spaces. To define a weakly small space, which is an analog of weakly definable, take an object of LSS, but now elements will be small closed, not small opens. Okay, now we mimic the definition that was given in the monograph by Cracow, weakly semi-algebraic spaces. An exhaustion is a family indexed by a partially ordered set A, such that the family covers X. It is increasing. Each element has finite height or infinitely many below it. The family is strongly downward directed, and the family of indexes is directed. If we have such an exhaustion, then members are called pieces. For a given exhaustion, we can define the induced lattice of closed sets or on a piece, the closed sets, the open sets, then admissible coverings or admissive families, and small sets. And it appears that always x of x is an object of this difficult category GTS. Okay. And this x of s of x of x will be called a weakly small space. But it's not a nice category. Some problems may appear. So for example, if we have the set of real numbers and the smopology is initial segments, then this gives us an exhaustion, but the whole set of real numbers, of natural numbers, is small closed, and it's not a subset of any piece, and also is small closed, but it's not a member of the smopology. So we need an additional axiom. A weakly small space is called nice if it admits both a smopology and an exhaustion being bases of the Bornology, right? Bornology, remember, it is an ideal of subsets, right? Such that its union is the whole set. So we assume that the small sets are generated somehow by the homopology Lx and by this exhaustion in P of X. If the space is nice, then the homopology is just the collection of small closed sets, and the family of all closed sets is just the sets compatible with this homopology. And this assumption of being nice is not very strong, because if we assume that the space is T1, exactly strongly T1, but only strongly T1 will be used here, it means that all singletons belong to this homopology. Then it is nice. And then all the possible exhaustions are equivalent. Okay, so if we have if you have weakly small spaces that are nice, and we want to make a category, right? So what are the morphisms? It appears that F being bounded continuous, F being strictly continuous, and F being inverse bounded continuous, which means if we reinterpret as locally small spaces, it is bounded continuous. Those three properties are equivalent. So those are our morphisms. So on the WSS, we have bounded continuous mappings, but on these nice weakly small spaces, right, any of these definitions can be applied. And also we have WSS1. Okay, and now the category of nice weakly small spaces admits a full embedding into locally small spaces. So again, it will be not needed to use general topological spaces. So if we have a weakly small space defined using Lx and this exhaustion, we forget the exhaustion and reinterpret these elements of Lx from small closed to small open, and it appears that the morphisms in the sense of nice weakly small spaces and locally small spaces are equivalent. So it's good to have such an theorem about full embedding. Okay, so now we can come back to definable spaces, and we glue together to get weakly definable spaces, object admitting exhaustions. Now a subcategory generated by nice objects and generated by strongly T1 objects. And the corollary is that all the theorems from the monograph by Knebusch, weakly semi-algebraic spaces from 89, and also all the theorems from this Rocky Mountain about weakly definable spaces are available using these definitions given here, without the use of generalized topology introduced by Dels and Knebusch. Okay, and also notice that there also an assumption of regularity was used in the definition of a weakly semi-algebraic or weakly definable space. Okay. So I have covered this two monographs, and in this third part, I want to speak about space of types, let's say, but with the spectral topology. So I want to get appropriate versions of stone duality. So recall that a topological space is coherent if the compact opens form a basis and are closed on the finite non-empty intersections. It is almost spectral, or some people call upspectral, if it's coherent and sober, including T0. It is spectral if it is compact and almost spectral, and it's Babs-Dwinger, it is coherent T0 and satisfies a condition which is called B-reducibility by Lorenzo Acosta. And the map between topological spaces is strongly continuous if it's continuous and the preimage of fundamental set is always fundamental. But in the context of upspectral spaces, fundamental is equivalent to being compact open. Okay, so what is the classical stone duality? The category of spectral spaces and spectral maps, which is the same as strongly continuous maps, and the category of bounded distributive lattices and their homomorphisms are dually equivalent. So one is equivalent to opposite of the second. And here some notations are used. We use the set of prime filters. We use H-ballet. Maybe this is important. If I have a homomorphism of bounded lattices, then the operation of taking the preimage of a prime filter is called H-ballet. And okay, the rest is standard. So this was in the 30s, yeah, of the 20th century, but also new versions of stone duality appear. So there is a Colombian mathematician Lorenzo Acosta, who has such versions. Define a homomorphism of lattices proper if the preimage of a prime ideal is a prime ideal. And he has the following version: Babs-Dwinger spaces and strongly continuous maps. This category is dually equivalent to the category of distributive lattices and their proper homomorphisms. Okay, and in a paper with his student in 2019, the category of almost spectral spaces and strongly continuous maps is dually equivalent to the category of distributed lattices with zeros and proper homomorphisms. Okay, so for me, it's nice to have my own versions for locally small spaces which are T0, small spaces which are T0, and the locally small spaces which are T0 and with special morphisms. So this last is the category of T0 locally small spaces and bounded strongly continuous maps. Strongly continuous means preimage of a SMOP is a SMOP. Okay. So those categories are equivalent we have those categories coming from the spectral spaces and coming from lattices. But let's first introduce Bornology on a bounded lattice. Bornology on a bounded lattice is an ideal such that its supremum is just 1. Okay, so what is this most complicated category spec BD? It's a triple, a spectral space, then a Bornology in the bounded lattice of compact opens, and a set called descent lamp, which satisfies those three conditions, right? Morphism is a spectral map between spectral spaces, respecting the descent lamp and satisfying a condition of boundedness. So, image of some element of the Bornology is contained in the Bornology in the this second space. I don't have enough time to consider what is the example, but the third condition is relevant, cannot be erased. Okay, those are these easier categories, just pairs, spectral space and a descent set. Descent means different sets, different compact opens, when restricted to this XD, are still different, right? And the morphisms are spectral mappings respecting the descent subset. By the way, descent subset is the same as patch dense, so the dense in the constructible topology. And this third category, USPETS DS, is a category of pairs of upspectral space and the descent subset, and morphisms are bounded strongly continuous maps. So again, a condition of boundedness as above, and pre-image of compact open is compact open, respecting the descent subset. And those categories coming from the lattices. Okay, so bounded distributive lattices with Bornologies and descent lamps. So bounded distributive lattice, Bornology on this lattice, and a set of prime filters satisfying the following conditions. And morphisms are homomorphisms of bounded lattices, which respect descent lamps and satisfy a condition of domination. And we have the other categories, just pairs, descent bounded distributive lattice and descent set of prime filters, morphisms, homomorphism of bounded lattices respecting the descent set, and here distributive lattices with zeros and set of prime filters, which is descent, and morphisms are dominating. This is analogous to this condition of domination. Dominating homomorphism of lattices with zeros, respecting the descent set of prime filters. So the proof, if you know what to what we want to get is not difficult. We have three functors. R is restriction functor, then S is taking a spectrum, and A is algebraization functor. So in the restriction functor, we restrict to XD, to the descent lamp, restrict also this family to D, and mappings are restricted to descent sets. In the spectrum, we take the set of prime filters with the usual topology, and we produce LS tilde and take the same DL. And the inverted homomorphism of lattices goes to this H bullet. And algebraization involves LX0. It is important that we cannot stop at LX. We need to produce LX0, right? Then we get equivalency. So LX0, the open set, the SMOPs, and X hat. And here is the operation of taking the preimage, which is easy, and we have natural isomorphisms. Okay, how much time do I have? So I have some bibliography here, but I don't know if it will be useful to say something about this monster category GTS. But it seems that I have some time, right?
Yes, you still have 3 minutes, or depending, or a bit more if you, depending on the questions.
But I started 10 past. Yes. So I have 13 minutes, right?
50 minutes. So. Oh yes, sorry. So you are still 10 minutes. Sorry.
Okay, so maybe I will tell something. So what is the history? In the 60s, Grothendieck introduced the Grothendieck topologies. So maybe pre-topologies are easier to describe with such axioms, which is completely abstract. Then it is not stated in these monographs by Detz and Knebusch, but in the 1984, in rigid analytic geometry, G-topologies were used. G-topologies are concrete versions of Grothendieck topologies. So we assume that we have some subset of the power set and inclusions are morphisms, and we assume that the covering families are families in the usual sense, right? And the products are taken from this P of X. So this means that intersection of two opens are opens. So these members of this family OP are objects of the category, are called admissible open sets, and we have admissible families of such objects, admissible or covering families. And usually G0, G1, G2 is added. And we get a continuous map between G-topological spaces. So preimage of open admissible set is open admissible, and preimage of admissible families and admissible family, right? Okay. So in 1985, those generalized topologies with 8 axioms were introduced. But what is the difference between the previous one is that finite unions of open admissible sets are admissible, and all finite families are admissible, right? So based on this, Delft and Knebusch produced this semi-algebraic homotopy theory. Now I want to put a simplified definition, but I need some notation, right? So finite subfamily, yes. So a refinement with the same union. This is family intersection, right? Family intersection. If I state this with a set, it means it is singleton on the side. And also sometimes, for example, sometimes family of families operations are used. And right, this is also an operation of families of families. Union 1 is the family of unions. Okay, so what is this simplified definition with only 5 axioms? It's this. A generalized topological space is X, set X, with open subsets and admissible coverings or admissible families, satisfying those axioms, right? Satisfying the axioms, which are quite complicated. Okay, then a map is strictly continuous if the preimage of admissible family is an admissible family. We get a category of GTS. It is a larger version of the category of topological spaces, right? So top fully embeds into category of partially topological spaces, which is a full subcategory of just generalized topological spaces. And so many notions have several variants. For example, there are weakly and strongly T1 spaces. And the key notion is smallness, right? A set is small if for each admissible family covering some open set U, if we restrict this U to K, it becomes essentially finite. So the family of small sets is a Bornology, and each strictly continuous mapping is a bounded mapping in these Bornologies. And a space is small if the whole X is a small set, which means that only essentially finite family open families are admissible. So SS is also can be described this way. Now we have gluing principle. We can glue generalized topological spaces if we have a family of such spaces intersecting along open subsets. Then on the union, we can introduce only one generalized topology such that those become open subspaces, and this family of UIs becomes admissible. And you have, so we can write X is the admissible union of these pieces, right? A space is locally small if X is an admissible union of some family of small opens, but also we can say of the family of all small opens. So we can get this LSS as a subcategory of GTS, right? LSS in the old language. Okay, so this is how operates this first theorem, and also Appendix 4. What is the use of locally definable spaces and weakly definable spaces? For example, our minimal homotopy theory. Okay, homotopy is a morphism from some space times a unit interval to another space. And what can we get? A large part of homotopy theory, which can be transported from the reals. So if we consider regular paracompact locally definable spaces, then it is the same as at least the homotopy categories are equivalent, right? So practically it is the same as regular paracompact locally semi-algebraic spaces. And even more homotopy theory is available if we pass to weakly definable spaces, because we have access to CW complexes, right? So the conclusion is that topological CW complexes, semi-algebraic CW complexes, and definable CW complexes, all these homotopy categories are equivalent. Similar facts hold for decreasing system of CW complexes. So we can transport from the reals to other models, right? Actually, from the reals to real algebraic numbers, and from real algebraic numbers to any other model. Okay. If we have models of some theory which are called bounded, bounded means for me that if I take the prime model and an element which realizes plus infinity, then this P of A has countable cofinality. Then also CW complexes, this category is equivalent to all weakly definable spaces over any model of T. So all the homotopy theory agrees with the usual one. And also, since we have CW complexes and pointed weak polytopes, so we can have generalized homology and cohomology theories, which are analogous to usual topological homotopy theory. Okay, so those are my slides. Thank you for listening, and I'm open to questions.
Thank you, Artur. Are there any questions? Or comments? Well, maybe just a naive question from my part. What is the difference between weakly small spaces and space with Bornologies? I was not sure to get it at the beginning of your talk.
Weakly small space?
Yeah.
Do we mean this, right? So
not might be nice or not nice. I don't know. Yeah.
yes, okay. So weakly small space is such a space that admits an exhaustion, right?
Ah, okay.
Of course, right? If we have such an exhaustion, then we have a GTS. Okay, and we have the notion of smallness.
Mhm.
So SMOPs, for example, for at the beginning, right, for locally small spaces, are just such open sets that are small. This somehow induces both open sets and small sets. In the weakly small spaces, okay, you need this axiom of being nice. If you have nice, then small set is a subset of a smopology, this Lx, or just a subset of some piece. So Bornology, the small sets is somehow a part of the structure.
Okay. Okay, thank you.
We need to also say what is open set, what is closed set.
Yes.
In the strong sense.
Are there other questions? Okay, well, let's thank Arthur again.
Thank you very much.
And I stop the recording.